Suppose R is a relation on A, and define a relation S on the power set of A as follows. S is going to consist of all the ordered pairs capital X, capital Y, where each of those is a subset of A, such that for all little x and big X, there exists a little y and big Y, such that X is related to little y by this relation R. Okay? And we're supposed to give a proof or a counterexample to justify or answer the following question. If the original relation R is reflexive, must this new relation S on the power set of A also be reflexive? Okay, let's try and draw a picture, see what's going on here. We started out with a relation R on A, and that means that R is a subset of A times A. So let's draw the Cartesian product of A with itself as a square. So this edge down here represents A, as does this one. Those are the two copies of A, and then any ordered pair in R will be somewhere in this square. Okay. Now we're going to try and assume that R is reflexive, and that what that means is for any x in A, basically the point x has to be in the relation, right? So you could we could represent the relation R by some graph here, or a bunch of dots, or whatever it is. So we must have that for every x, and what that means, if you draw all those points, is that basically we must have this diagonal here. I wonder if I can actually draw this. Let's see. There we go. Okay, let me try that one more time, see if I can get a little straighter. Okay, not terrible. R being reflexive means that R contains all the points on that diagonal. Okay, and so we have that, and now we're trying to figure out if S is reflexive. So we should take some set capital X in the power set of A. In other words, X should be a subset of A. So maybe I'll take it somewhere in the middle of A here, right? It's basically this piece, and then I'll draw that same X in this other copy of A over here. Try to make it about the same length, okay? And then, okay, so we're supposed to look at the ordered pair X, and we want to know for all X in the first copy of X, so for every X in here, does there exist some Y in, well, in capital Y, but that's just X for us again, because we're trying to figure out whether X is in S, right? So instead of X and Y, we had just X and X. So does there exist some Y in here such that the ordered pair X, Y is in R, right? And sure enough, there does, because here we have this point which is in R, which corresponded to taking the same little x as the second coordinate. Okay, so we're using precisely the fact that little x is in big R to get that big X is in S. Okay, so it seems like it's true. It seems like S is reflexive. Let's try and work out the logic just to make sure. We have R is a relation on A, and then I'm going to go ahead and suppose that R is reflexive for direct proof, and our goal is to show that S is reflexive. R being reflexive means that for all A in the set A is related to itself by R, and S being reflexive means the same thing, but now my set is power set of A, and so talking about subsets of A, I'm going to use capital X for that variable. Good. Now we have two universal quantifiers. In that situation, I want to do the one on the goals side. I want to let X be an arbitrary element of power set of A, and I will prove that XX is in the relation S. And we know that being an element of the power set means X is a subset of A. And then to decide what this means, right? And remember, that's just a different notation for saying that capital X is in the relation S, and S is defined up here, right? So S is a set of all these such things, such that for all x in X, there exists Y in, again, capital X in our case, such that X are Y. So that's what we have here, although you'll see instead of a little y, I decided to use an x prime, since it is, after all, another element of capital X. Okay, so I have two elements in capital X and X prime. All right, and there's a universal statement we're trying to prove, so we can let X be an arbitrary element of capital X, and then we have this existential statement left over to show. So we need to find some x prime in capital X such that this statement would be true, and x looks like a good candidate, right? Little x. Because, well, going back over to our givens, if x is in capital X, and capital X is a subset of A, then x is in A. And so we can do a universal instantiation. Before we do that, let's go ahead and say, okay, we're going to prove that where x prime is little x. And now to finish it off, we do universal instantiation on this statement here using x in the place of little a, and we get exactly x Rx. Okay, so basically the same argument we were trying to illustrate with our picture. Well then, let's try and type out the proof here. So remember, we originally had a conditional that we were trying to prove, and I started out by taking the antecedent over as a given. So we should say, suppose R is reflexive. We show that S is reflexive. Good, so that brought us here, and then we did a definition, and then we had to let X be an arbitrary element of power set of A. So that brought us to that and left us with this goal. So let me say let X be an arbitrary element of power set of A. We show that X is in S. Okay, I mean, I'm just rewriting this in different notation. I like this one a little bit better in this case because having three capital letters in a row there, when you first look at it, it's not 100% obvious that S is a relation and the X's are the elements of the power set. So either one's fine though. We're going to show that i.e. that, well, let me just right away go ahead and bring this down to here. It's just a definition, so we can just add it on. But we should probably type it out so that our reader remembers what that definition is. So say for all x in X, there exists an x prime in capital X such that X is related to X prime. All right, now you might be mad at me for putting some logical notation in my proof here, but the reason I'm okay with that here is that it was given to me in the definition of this relation S in the problem, right? So I think it's okay to bring that in here so that the reader can sort of match those up in their mind. All right, and where does that leave us? Well, okay, so we're trying to prove that, and then we had to let X be an arbitrary element of capital X. And we're going to show the existential statement. So that's our next comment. Let X be an arbitrary element of capital X. We show that there exists X prime in X such that X prime, let me get this right here, such that X is related to X prime. Okay, just copying from the other side. And very good. And finally, we just got to seal the deal. So if you write out the definition of X being a subset of A, then modus ponens together with the X in X with modus ponens gets you to X in A. And then we did a universal instantiation to get our goal. All right. So let's write down those two steps. because x is an x and x is a subset of A, it follows that x is also an A. And because, well, where did this universal statement here come from? That came all the way up here from, that's the definition of R being reflexive. Okay, so that's what I should mention. Because R is reflexive, this, meaning what I just said, that x is an A, implies that we can do a universal instantiation and we get x R x. Okay, and so if you look on our last two lines, we have that x is in A, and actually we have x in x back here, right, which matches up with this part, and then we have x Rx right here. Okay, so I don't know, if we want to be extra clear, maybe we should say that because x is an x and x Rx, it follows that this thing we were trying to prove is true. Okay, this last line is kind of optional, but it probably doesn't hurt to put it in there just to make sure the reader understands that we're done. Okay.